All right, strap yourselves in, because today we are diving deep into the mind-blowing world of Einstein's theory of special relativity.
A deep dive indeed. We are taking on his groundbreaking 1905 paper on the electrodynamics of moving bodies.
No biggie, Einstein.
Right.
Just casually revolutionize our understanding of space and time, Tuesday stuff.
And revolutionize it, he did. This paper really is a pivotal moment in scientific history. I mean, Einstein didn't just tweak existing theories here. He completely rewrote the rules of the game.
So what was going on in the physics world that sparked such a radical shift? Was there like a big physics conference? Did everyone get together and decide things were too boring?
Well, it wasn't quite like that. Imagine you've got these two titans of physics, right?
Yeah.
Newton's laws of mechanics, they work perfectly for describing, everyday motion.
Apples falling from trees, that sort of thing.
Exactly. And then you've got Maxwell's equations. They elegantly explain the behavior of electricity and magnetism.
Okay, so far so good. We've got motion figured out. We've got electromagnetism figured out. Everyone's happy, right?
Not so fast. The problem was these two giants of physics, they didn't always see eye to eye. When applied to objects in motion, they sometimes gave contradictory explanations.
Oh, like trying to assemble a piece of furniture with instructions written in two different languages, both claiming to be correct?
Precisely. And one of the most glaring contradictions had to do with how classical physics explained the interaction between a moving magnet and a conductor.
Okay, so we've got magnets, we've got conductors. Things are getting interesting. Break it down for me. What was the issue?
All right, so picture this. You have a magnet and a wire. If you move the magnet near the wire, you generate an electric current. Pretty straightforward, right?
It seems simple enough.
But here's the thing. It didn't matter whether it was the magnet moving or the wire moving. The outcome was the same.
The relative motion between the two is what counts, right?
Exactly. But classical physics, it had different explanations depending on which object was considered at rest. It was a sign that something was fundamentally off about our understanding of motion and how it related to electromagnetism.
This is where Einstein steps in, ready to drop some serious knowledge bombs and shake things up. So how did he resolve this contradiction? Did he pick a side, team magnet or team wire?
He took a much bolder approach. Instead of trying to modify existing theories, Einstein took a more fundamental approach, establishing two postulates, two deceptively simple statements that would send shockwaves through the world of physics.
Okay, hit me with these two postulates that changed the course of physics.
The first one states that the laws of physics are the same for all observers in uniform motion.
Meaning, it shouldn't matter if you're standing still, walking, or even flying through space at a constant speed. The laws of physics should apply the same way, right?
Exactly. Now, get ready for the second postulate, because this is where things get really wild. Einstein stated that the speed of light in a vacuum is constant for all inertial observers.
Inertial observers. Okay, time for a quick vocab lesson for our listeners, myself included, who might not have a physics dictionary on speed dial. What does that even mean, inertial observer?
Sure, an inertial observer is simply someone who's moving at a constant velocity. So imagine you're cruising in a car at a steady speed or floating in space far away from any planets or stars that could tug on you with their gravity. You'd be an inertial observer.
Got it. So back to the speed of light. Einstein is saying no matter how fast you're moving, even if you're approaching the speed of light itself, light will always appear to be moving at the same speed to you.
Precisely. It doesn't matter if you're moving toward a beam of light or away from it, its speed remains constant. And I get why that might seem counterintuitive. We're used to the idea of, speeds being relative, like if you're driving towards another car.
Right. It seems like it's coming at you much faster. But light doesn't play by those rules according to Einstein.
Exactly. And this seemingly simple statement has some truly mind-bending implications for our understanding of space and time.
This is where we get those classic Einstein thought experiments, right?
Yeah.
The ones that make you question everything you thought you knew about reality.
Absolutely. One of the most profound implications of Einstein's postulates is that simultaneity, the idea of events happening at the same time, is not absolute. It's relative.
Okay, hold on. You're saying that your now might not be the same as my now. That's messing with my perception of reality a little bit.
That's the beauty of special relativity. It challenges our everyday intuitions, and to illustrate this whole concept of relative simultaneity, Einstein came up with a brilliant thought experiment involving a train, lightning strikes, and the very nature of now.
All right, lay that thought experiment on me. Paint a picture with your words. Help me visualize this.
Okay, so imagine you're standing on a train platform, just watching as a train speeds past. Okay, so you're on that platform. watching the train speed by, and at that exact moment, two bolts of lightning strike. One at the front of the train, the other at the back.
Okay, I'm picturing it lightning strikes, very dramatic.
Now, because you, the observer on the platform, are standing exactly halfway between those two lightning strikes, the light from both reaches your eyes simultaneously.
Equal distance, light traveling at the same speed. I'm seeing two simultaneous lightning strikes. Makes sense.
Precisely. But now let's change our perspective a bit. Imagine there's another observer, but this one is on the train, also positioned right in the middle of the train car.
Okay, I'm starting to see where this is going. The train's moving towards one lightning strike and away from the other, so that observer wouldn't see those strikes as simultaneous.
You got it. The light from the lightning strike the train is approaching is going to reach the observer's eyes first because they're racing toward that light. The light from the strike at the back of the train, that's going to arrive a little bit later because the observer is moving away from it.
So the observer on the train sees one lightning strike happen before the other, while to me on the platform, they happened at the same time. That's wild. It really is, like you said, my now isn't the same as theirs.
It's a mind-blowing concept, isn't it? Time isn't this rigid, universal thing. Our experience of now depends on our frame of reference, on our relative motion.
Okay, that's incredible.
Yeah.
But I know this isn't just some philosophical thought experiment. There are actual measurable consequences to this relative nature of time, right?
Oh, absolutely. Einstein's special relativity, it goes beyond thought experiments. It gives us concrete, testable predictions. And this leads us to two of the most famous consequences of special relativity: time dilation and length contraction.
Okay, those terms sound kind of intimidating, even though I know they're about to blow my mind. Can you break those down for us?
Sure. Let's start with time dilation, which means that time itself actually slows down for objects that are moving at speeds approaching the speed of light, relative to, of course, a stationary observer.
Wait, slow down, you mean time itself, so a clock in motion would actually tick slower than a clock at rest.
That's exactly it. Imagine you have two identical clocks, right? And you send one of those clocks on this high-speed journey a significant fraction of the speed of light.
Okay, picturing this epic space voyage for one very special clock.
When that speedy clock returns, it's going to show less elapsed time compared to the clock that stayed put.
It's not that the clock malfunctioned or anything. Time itself actually passed slower for that clock during its high-speed journey.
You've got it.
Yeah.
I realize this might seem completely counterintuitive. We don't experience time slowing down or speeding up in our daily lives.
Yeah, it's not like our watches suddenly start running backward when we hop on a plane.
Right, and that's because the effects of time dilation are really only noticeable at speeds approaching the speed of light. But, and this is the really cool part, even though we don't experience them directly in everyday life, these effects has been experimentally verified.
Really? Tell me more about that.
Well, scientists have actually flown highly precise atomic clocks in jets around the world and then compared them to synchronized atomic clocks on the ground.
And what did they find? Don't keep me in suspense.
The clocks that traveled at high speeds, they ticked slightly slower than the stationary clocks, just as Einstein's theory predicted.
Okay, that is just mind-boggling. It's like science fiction, except it's real. So we've got time dilation. What about length contraction? How does that fit into all of this?
Well, length contraction means that the length of an object moving at speeds close to the speed of light, as measured by a stationary observer, will appear to contract in the direction of motion.
Wait, you're telling me that objects actually shrink when they move really fast?
That's right. The faster an object moves, the shorter it appears to be in the direction it's traveling. Again, to someone at rest.
Okay, now I need an example. I'm having trouble picturing this.
Okay, imagine that spaceship you mentioned earlier blasting off to a distant star.
Let's call it the Cosmic Cruiser. I like the sound of that.
Perfect. So the cosmic cruiser is traveling at, let's say, a significant percentage of the speed of light, right? To an observer on Earth, that spaceship would appear shorter, compressed in the direction it's moving.
So it's like the faster it goes, the more squished it gets.
You could say that, yeah.
Yeah.
But, and this is important, this length contraction is relative. To someone on board the cosmic cruiser, the spaceship would appear perfectly normal. It's only from the perspective of that stationary observer that the length appears to change.
So to bring it back to time dilation, it's all about the observer's frame of reference.
Exactly. The closer an object gets to the speed of light, the more pronounced these effects of time dilation and length contraction become. And this leads us to another incredible implication of special relativity.
Go on, I'm hooked.
Einstein's equations show that nothing, and I mean nothing, can travel faster than the speed of light in a vacuum.
Hold on, there's a cosmic speed limit, and it's the speed of light. But why? Why is that the magic number?
Well, it comes down to the fundamental nature of space-time itself. The speed of light isn't just about how fast light travels, it represents the ultimate speed limit for anything in the universe, for both physical objects and even the propagation of information itself.
Okay, that is a truly profound concept. We're not just talking about putting a governor on spaceships here. We're talking about a fundamental limit woven into the fabric of the universe. This
Huh.
is heavy stuff.
It is. And there's still one more mind-blowing piece of the puzzle we need to explore, EMCAC. But I think we've covered enough ground for now. How about we take a quick break, let our listeners process all these mind-bending revelations, and then come back to tackle that very famous equation.
Sounds good to me. We'll be back in a flash well. Not quite at the speed of light, but you get the idea. And we're back, listeners. It's kind of mind-blowing to think about how these ideas we've been discussing, these fundamental concepts about the universe, were once considered radical, almost heretical even.
Oh, absolutely. Einstein's work on special relativity really did revolutionize physics, but I think what's even more amazing is how well his theories have stood the test of time. Over a century later, they're not just accepted, they're the foundation for countless scientific advancements.
Speaking of that lasting impact, what are some of the ways special relativity is still shaping our understanding of the universe today?
Right.
Where can we point and say, that right there, that's Einstein's legacy?
Well, for one, special relativity is absolutely crucial to modern cosmology. The study of the universe on the grandest scales. It helps us understand everything from how galaxies behave to the very evolution of the universe itself.
Okay, so it's helping us answer some of the biggest, most fundamental questions about where we come from and where we're headed. That's huge. But it's not all just about understanding the cosmos, is it? Are there any more down-to-earth applications of special relativity?
You're absolutely right. It's not just theoretical. It might surprise you to know that special relativity actually plays a vital role in technologies we use every single day. Take GPS, for example.
Okay, sure, GPS. I get the basic idea. It uses satellites to pinpoint your location. But how does Einstein fit into all of this?
Well, those GPS satellites, they're moving at incredibly high speeds, and they're also further away from Earth's gravity compared to us down here on the surface.
And that affects time. Wait, this is about time dilation, isn't it?
Ah, you got it. Those GPS satellites actually experience time slightly differently than we do here on Earth.
So their clock's running slower.
Well, slower because of their speed, but get this. A tiny bit faster because they are further from Earth's gravity. Both special and general relativity have to be taken into account.
So to get an accurate GPS fix on your phone,
Hmm?
we have to account for Einstein's theories.
That is wild. It's pretty amazing, right?
Yeah.
And that's just one example. Special relativity is also essential in fields like particle physics,
Yeah.
where scientists are studying the tiniest building blocks of matter.
So we can thank Einstein for helping us unlock the secrets of the subatomic world, too. It's amazing how these seemingly abstract theories have had such a concrete impact on our lives.
Absolutely. And of course, we can't forget about the most famous equation of all time, EMC0.
Ah, yes, EMC arrow. It's become so iconic, even people who don't know the first thing about physics have heard of it. But what does it actually mean? Break it down for us.
In essence, it tells us that mass and energy are fundamentally equivalent, two sides of the same coin. Mass can be converted into energy, and vice versa.
And that's the key to things like nuclear power, right? A tiny amount of mass can be converted into an enormous amount of energy.
Exactly. And it works the other way around, too. Energy can be converted into mass, which is actually what happens in particle accelerators.
Yeah.
These high-energy collisions we hear about, they can actually create new particles.
Wow, it's incredible to think about how this seemingly simple equation, EMCI, really represents a paradigm shift in our understanding of the universe.
It really does. It's just one of many profound insights that came out of Einstein's 1905 paper on special relativity.
So as we wrap up this incredible deep dive into the mind-bending world of Einstein's work, what's a final thought you can leave our listeners with? Something to ponder as they go about their day, maybe contemplating the nature of space and time.
Well, we've talked about how time slows down at relativistic speeds, right? So here's something to chew on. Imagine, just for a moment, that we could develop spacecraft capable of traveling at speeds approaching the speed of light.
Okay, I'm picturing humanity finally venturing out into the cosmos, exploring those distant stars and galaxies.
What if, by harnessing the very principles of special relativity, we could effectively make those interstellar journeys shorter, at least from the perspective of the astronauts on board? Could we, in essence, use time dilation to our advantage? allowing humans to traverse the vast distances of space within a human lifespan.
Wow, that's an incredible thought. It's like we could cheat time itself to unlock the secrets of the universe. Now, that's a concept worth pondering.
Indeed. Who knows what the future holds? But one thing is for sure. Einstein's legacy of questioning, of exploring, and pushing the boundaries of human understanding, it's going to continue to inspire generations of scientists and dreamers for centuries to come.
And on that note, we'll wrap up this incredible journey. We want to thank you, our amazing listeners, for joining us on this deep dive into the fascinating world of Einstein's special relativity. Don't forget to check out the source material for yourselves, and until next time, keep questioning, keep learning, and most importantly, keep looking up.